So we started looking at phase detectors for data. What I said earlier was that we have a phase lock loop that is capable of tracking the phase of some periodic signal that we arrived at by having a VCO and a loop filter and a phase detector, and also a frequency divider and the feedback path. The frequency divider, of course, is optional. If you want the output frequency to be the same as the input frequency, then you don't need a frequency divider. Okay. Now, what I am saying is you have only the data, you don't have the clock with which you can retime the data. So, to obtain the clock, you can use exactly the same arrangement, but using a phase detector which works for random data input, right. Now, the phase detector should not detect the phase difference between two periodic signals, but it should detect the phase difference between a random data at a certain rate and a clock at that frequency. Okay. In the scheme, we kind of half came up with the scheme yesterday, and the idea was, let's assume that the clock frequency and the data rate are the same. Okay. So maybe the data is like this. So each of these represents one period of data. Okay. And the clock, it can be out of phase. So this is one cycle of the clock. And let's say we are interested in the phase difference between the transitions of data, either rising or falling, and the rising edge of the clock. Okay. So the scheme we came up with was to clock this data, clock a flip-flop with this data input, so that the data edges are aligned to the clock edges. Essentially, now you get two data waveforms which have the same bit transitions, but which are phase shifted from one another, and the phase shift equals the phase difference between the data edges and the clock rising edge. Okay. And this much we can obtain by having a flip-flop which is clocked with the clock and the input is data. Okay. And how do we measure the phase difference? A measure of phase difference is obtained by XORing these. Okay. So yesterday there were questions about duty cycle and so on. So what is the, like, which duty cycle are we talking about? Is there a problem here? So in this case, like the data is periodic with some period and the clock has the same period, let's assume. So in that case, we are shifting the same data, right? So there is no issue of duty cycle. It's not like two independent signals which have different duty cycles and you have an issue with phase detection. Okay. So what do we get out of this XOR? It will have pulses. Let me assume that it is logic states are 0 and 1. And sorry. So every time there is a transition, there is a pulse whose width equals the phase difference between clock and data. Okay. So can we use this in our PLL? So let's say we have our usual charge pump, loop filter, okay, and a VCO. Now, when you are doing clock recovery, the clock rate of the VCO is same as that of the data. Okay, there will be no divider in the feedback part because you want to clock the data in every period. Okay. So that is one difference. Is this part clear? Why there is no divider in the feedback part? Because you are trying to recover the clock at the frequency of the data, not at some multiple frequency at a multiple of the data rate. Okay. So you don't need a divider here. You just have this. Now my question is, can I use this as a phase detector? Okay. So this is the clock and I have the data here. Can I use this and then apply this to the charge pump? Huh? Produces only one direction signals. Okay. So how do we get the other output? So fine, what do we finally want to happen to this clock? Where should this clock be? The rising edge of the clock? Aligned to the data edge or the middle of the data? Middle of the data. Okay. So of course, the other thing you can assume, which is different from in case of a frequency synthesizer, is you take the output of the VCO directly. So it is reasonably safe to assume that you have 50% duty cycle here. Okay. It won't be exactly 50, but it will be more or less 50. Especially at high frequencies, you use an LC oscillator to make the VCO. When you use an LC oscillator, the waveform is almost sinusoidal. And if you have a sinusoidal waveform, it does have a 50% duty cycle, right? The successive edges are half period apart. That is, the rising edge is half period away from the falling edge and so on. Okay. Whereas if you put this through a divider, because the divider is a counter, especially when you have odd numbers, you can have other duty cycles. Okay. So here we have 50% duty cycle. So it's okay to align the rising edge to the edge of the data. In that case, the middle of the well, actually, in this case, the falling edge will be in the middle of the transition. No, actually, that is not a good thing because I take that back. The rising edge has to be in the middle of the data because, see, you want to delay the data, right? So that means that you have to detect the data correctly. To detect the data correctly, the rising edge has to be in the middle. Okay. So if it is near the edge, it will detect something near the zero crossing. And also, other thing to keep in mind is that the data waveform will not be like this, right? Output of the equalizer will probably look something of this sort. It will be some smoothed out version in reality. Okay. So if you try to, if you clock it somewhere here, you will get just some noise or some small signal. So you don't get the data exactly. Okay. So the clock must be in the rising edge of the, the clock rising edge must be in the middle of the data period. Okay. Now, when does this loop lock? When does it reach steady state? What is the condition for steady state? No, that we can't say about the phase difference here. I mean, that depends on the type of phase detector, but when, like, what is the so this the control voltage should be steady. That is steady state, and that in turn means that this current is 0 on average. Okay, the current flowing out of the charge pump. So what we want is an arrangement where when this rising edge is in the middle of the data period, this current is 0. Okay, and the charge pump has up and down inputs. How do we do that? Okay, firstly, let's, so we need two inputs up and down, and they should be such that when it is locked, I mean, basically this charge pump output current is 0 when the rising edge is in the middle of data. So how do we get is this the up or down input, and how do we get the other one? Huh? What's that? Between what and what? Okay, that is, yeah, that is possible. No, but that will do it only at one of the edges, right, of the data. Because that will, so there it was measuring the phase difference between rising edges or falling edges. So, I mean, that will still work, but you will lose half the information, meaning there is phase difference information in the rising edge of the data as well as in the falling edge of the data. So, you would like to use both. But yeah, it is possible. Let's see what the effect of that is afterwards. Okay. So, XNOR, okay. XNOR between this and this. How will that, so up and down will be opposite of each other, right? Yeah, it will just. We remove the phase shift between what and what? Okay. No, fundamentally if you have an XOR and XNOR, the outputs are equal and opposite, right? The charge pump current output will be 0, isn't it? Like both switches will be on or both switches will be off. Well, I mean, in this case, the locking point is in the middle. Okay, so if it's the up minus down that goes into the charge pump, right? That must be 0 when it is aligned exactly to the middle. That's what you want. You have use an XOR. What's that? You use. Okay. And okay, what will that give you? That will give you a phase transition? No, I didn't understand that. See, the XOR output is already active only when there are transitions in data. Okay. No, also I want the output of the charge pump to be 0 when the clock is aligned to the middle of data. Okay. Okay. See, actually, if we AND which one? This and this. Okay, what will we get? No, okay. And then what do you do with it? Yeah, I think actually maybe this discussion is going in a very complicated direction. But anyway, let's. So this is the XOR output. Okay. So what I was trying to get at was something much simpler than that. And this is the phase difference phi. So if I plot the average of the XOR output with phi, what do I get? Huh? What is it when phi is 0? 0. Okay. And as I increase phi, what happens? Huh? Maximum at? Pi by 2 or pi. 2 pi. See, this is one period. So this is my 2 pi. Okay. So when is it maximum? At pi. Why? See, when this reclock data is somewhere here, okay, I get the maximum, right? Isn't it? Huh? Yeah, not negation, one shift, one period away, right? That's data, you can't say that it's exactly negative. So, it does something like this, okay? Now, when did I say I want 0 output? For, what is the phase shift I want to lock at? Pi, right? So, all I need to do is to subtract this much, isn't it? So, that's all I was trying to get at. So, this phase detector gives you a positive output starting from 0 as you shift the phase. But I want, the output I want is something like this. Okay. So, I want to get this difference. How do I get that? Use a negative edge triggered flip flop. What is the input to the flip flop? Okay. That will give us that. Yeah. So that is the problem, right? You can't sample D at the falling edge. That's not a good thing. So what do you sample at the falling edge? Is this? Yeah. So essentially I want to get the average value, right? But I make a flip-flop using some transistors and I don't know the exact average value. I know that I'll get a pulse. Okay, that pulse depends on the flip-flop itself. So it would be best if I get that average value or this shift using a flip-flop itself, so that it will be exact. So how do I do that? Yeah, that's exactly what we need to do. See, when it is shifted by pi, when the clock is aligned here, this XOR output will be half period wide. Okay. Now, we need another output which is also half period wide, and then that will cancel out this one. Okay. No, what I was saying is when you don't know the average exactly. So, let's say the output of a flip-flop will look something like this, okay? The output of the flip-flop and XOR. Now, it's not, if it was something like this and you knew this value exactly, you could use an DC source and compute the average. But if it is like this, you don't really know that, okay? And also, you're not interested in knowing the absolute value of the average. You want to get another waveform which has the same average as this one, okay? Yeah. No. I mean, then there will be no DC at all, right? You mean you want to do this? Yeah, but like what will be the DC voltage here in that case? It will be 0 always, isn't it? So the output of this XOR gate will be pulses which are half period wide when the clock is aligned to the middle of data. Okay. Now I don't want to feed that directly to the charge pump because that has a non-zero average. In fact, I want to feed that as the up signal and some identical waveform as the down signal so that it becomes 0. Okay. At least 0 in the average sense, not instantaneously 0. Okay. So the idea is to use another clock, and here we rely on the 50% duty cycle of the clock. So this is the rising edge, this is the falling edge triggered flip flop. And we do this. Okay. Now there are several practical things that make this a good phase detector. That is, you are getting this pulse, the subtracting pulse, in exactly the same way as you do this. So all of the non-idealities, the shape, weirdness in the shape of that you see in this pulse will also be there in this. So the cancellation will be better. I mean, there may be other ways of getting a half period pulse and trying to subtract it. But in that case, the pulse shape may be slightly off. Okay, you will have a bit of a problem. So what is the output of this XOR? How does it depend on the phase difference between the data and clock? Doesn't depend on the phase difference, because this is data clock with the rising edge, this is data clock with the falling edge. So what you are going to get here is half period wide pulses whenever there is a transition in data. And the output of the first XOR gate depends on the phase difference. That has pulses whose width equals the phase difference whenever there is a data transition. So you use this as one as the up signal, the other one as the down signal, and you are set. Okay? Is this okay? So the effect of using this as up and this as down is simply shifting this average characteristics down by that much. Okay? Is it okay? So let's say this is our data and this is clock. Okay. Then the up signals will be, and there is no transition, it's missing here, and then you have this. And the down signals will be what? It will start at the, basically it will give you something like this, right? Okay. Yeah. 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 So first of all, in this case, where is the reference? The reference is the data, right? So these considerations are different for frequency synthesizer and for clock and data recovery circuit. Okay. In a frequency synthesizer, you are trying to get a purely periodic signal without any disturbances. So you don't want the reference feed through. In this case, I mean, it is true. So in steady state, there are disturbances. Okay. So you would like to maybe avoid it, but in this case, it's not as critical because the input is data and you are supposed to align the clock with respect to the data. Yeah. So what I'm saying is the purity of the sine wave that you need in this case is not as much as the purity of the sine wave that you need to generate as a reference signal, okay, in a radio or something. See, what happens is, yeah, you have this clock and the clock is supposed to be here. Because of all these disturbances, it will move a little bit from this. As long as it is not too much, it is okay. And that how much is too much is much more in the clock recovery case than in the frequency synthesizer case. Okay, you can tolerate a lot more jitter in the clock recovery case. And there will be more jitter anyway because of the changing data pattern and so on. Okay. In fact, in a way, it is better that it responds to the data edges because sometimes because of ISI and so on, these the data edges are not separated by integer multiples of the period. That you know from your simulations of ISI, right? So, or some other, the data itself can have jitter. Now, what happens is in the clock recovery, in a frequency synthesizer, it should try and reject all of the jitter and give you a pure periodic signal. In this case, if the data has jitter, you had better track it. Okay, because if the data pulse instead of coming here, comes here, then the clock and data recovery circuit, instead of retiming it here, it should time it here. So it should respond to jitter in data also. So some of that, this aspect which looks like reference feature is good for a clock and data recovery circuit. Okay. So you want to track some of the jitter in the data. Because the long-term jitter in the data can be quite a lot. Okay. Because of the jitter in the transmit source and so on. So now if you clock it with a perfectly periodic signal, you may end up with a problem. Let's say you know the average frequency of the data, so you somehow magically get exactly periodic signal with that average frequency. You clock it, now the data is jittering back and forth. So you are clocking it at different points of the bit period. And the total data jitter could even be more than one bit period in the long term. So you are sampling the wrong bit. Whereas the clock and data recovery circuit should do better than that, in that it should track the jitter in the data and go wherever the data is moving and track retime it. Okay. But it is true that the charge pump is not quiet, whereas in a frequency synthesizer, when it's perfectly in lock with the ideal ideal phase detector and charge pump, the input to the charge pump is 0. So there is no activity there, it's quiet. Whereas in this case, it's not. When it is locked perfectly, it has up is half period pulse and down is a half period pulse. So there are ways to improve the jitter because of that, okay, without compromising the tracking property of the clock and data recovery circuit. Is this clear? So if you understood the general principle of phase detection, there is not much complicated with this. You can take this phase detector, put it in place of the phase frequency detector, drive it with data, and it should be able to lock it. Okay. Yeah. What will happen in that case? What happens if there are mismatches in the current source? It has to be, right? So the average value has to be 0 for locking. So that means that there will be a phase offset in the locking. Okay. So meaning it won't, when this is half period wide and this is half period wide, when up and down are half period wide pulses, the average current is not 0. Maybe the average current is 0 when up is slightly more than half period and down is slightly less than half period. So the clock will align to something that is later than the midpoint of the data period. Okay. So the effect of mismatch in charge pump is basically a phase offset in steady state. Okay. So this is a linear phase detector that works for data, and I think this was proposed by some Mr. Hogg. So it's called the Hogg phase detector. Yeah. No, it won't work, right? It has to be, the data and clock have to be at the same rate. Why would you want to do that? So, okay, it is always possible that you overclock at the receiver. That is, you sample the received data at a much higher rate. Okay. That is definitely possible, but firstly there is no motivation to do that. You are already transmitting at a high speed. So if you are transmitting at 10 gigabits per second, you don't want to sample at 100 gig and get lots of samples. The second thing is, if you are really oversampling by a lot, let's say you are transmitting at 100 megahertz, but you are sampling at 1 gigahertz, you actually in that case don't need a clock and data recovery circuit in the analog domain. Okay, you can get the samples. So if you do that, you know that you are going to have these samples. It's okay if they are misaligned a little bit, and you get these. From the recovered data, you can anyway reconstruct from the recovered samples, you can anyway reconstruct the data. So the clock and data recovery circuit can be done digitally or in some other way. Okay, sometimes you do that. You do what is known as blind oversampling. You just take a lot of samples, and after that you digitally see where the data is going. Okay. So if you have an analog type of technique, then you can't uniquely define it, right? So if you have clock at twice the data rate, you will get something similar. Okay. So in fact, many circuits have this problem of locking to the harmonics. So if you send a clock at twice the rate, exactly twice the rate of the data, then you will get more or less similar output, and then it may lock. Okay. But usually that doesn't happen because you don't clock it at such a high frequency. When you are already transmitting at a high frequency, you don't have something that goes to a high frequency. Also, when you design it, right, when you have a VCO, it is not likely that if you design it for 5, it will go to 10 and then it will lock to the harmonic or something like that. Okay. Okay. So this can, that's true. This works for binary data. So for PAM data, see, one simple thing that you can do is you can just use it as it is. Okay. So it will give you something, right? I mean, basically you treat the PAM data like binary data. If it is less than 0, it is logic 0, and if it is more than 0, it is logic 1. So you can do that. Maybe you will lose some of the transitions and so on. You will not detect the transitions between. So what I am saying is you just convert the PAM data into binary data as far as clock recovery is concerned. So in that case, some waveform that is like this. So you will lose these transition information, and you will work only on these transitions. Okay. So basically, the number of transitions to work with is less, and we'll see what the effect of that is. So that is one possible thing to do. Okay. But there is see, when you make you can think of this as a slicer for binary data, or the decision maker for binary data. You have a similar decision maker for PAM data, which will consist of more flip-flops, right? You will have offsets and flip-flops, because you want to also distinguish between these two. Okay. So there will be one comparator whose threshold is here, another one whose threshold is here, and so on. So because of that, you do know all of the transition information. So by combining all of those things, you can in fact come up with something similar to this. Okay. So essentially, you have the detector, and then it will be more complicated than for binary data. Similarly, if you want to clock it with some offset, that part also will be more complicated than for binary data. By combining all of that, you can get a phase detector that works on all of the transitions of PAM4 data. Okay. But you can just feed PAM4 data here and it will lock. But the properties of the phase lock loop will be somewhat different, because you have lost a certain number of transitions. If all transitions are equally likely, then you have lost half the transitions. What is the effect of that? So let's say, what do you think will happen? So the clock and data recovery circuit is crucially dependent on the number of transitions you have, right? You can't have transition density that is, or can you have transition density that's very low? If you have no transitions at all, there is no meaning to clock and data recovery circuit, right? So what happens when the transition density is low? By transition density, I mean the best transition density is when you have 1010 pattern. Of course, that is useless data. If you already know it's 1010 pattern, you can generate it for yourself. There is no need to transmit that thing. Okay. So that we define as a transition density of 1. Okay. Now, random data will have a transition density of half. Every bit can be either 0 or 1. That means that if this bit is 0, the following one can be either the same bit or another bit with equal likelihood. So the transition density is half. And similarly, you can arrange the data to have different transition densities. Okay. So what is the effect of transition density on the clock recovery circuit? What do you think will happen? Yeah, essentially it is to do with the bandwidth of the locking process of the phase lock loop. Okay. If you have very few transitions, it will take a long time to acquire lock, right? So because you get information about the phase difference here, let's say, and if your next transition comes only tomorrow, then it has to just hold that phase till tomorrow and then update the correction afterwards. Okay. That is one consequence of having if you have low transition density, you will have low bandwidth. That is, it takes a long time to lock. Okay. In fact, you can think of the average output of the phase detector as If you look at the output of this, it is pi by 2 pi, but it's pi by 2 pi when there is a transition. So if you want, you can represent the same thing as pi by 2 pi times the density factor, right? That is the overall average of the phase detector output. Okay, so what is this? This is like reducing the gain of the phase detector, isn't it? In case of the frequency synthesizer, we don't have this. The density, the transition density is 1. Okay, in this case we have that also, so that multiplies the phase detector gain. So essentially the phase detector gain is multiplied by the transition density. So that directly appears in the bandwidth of the phase lock loop. Okay. So the linear phase detector in the assignment is supposed to be this. Okay.
In that case, what if it belongs to a clock frequency that is a divided version of what you need?
Well, then you will be losing data, right? Meaning, if you, why would it do that?
Your clock period ends up being more.
Okay. Yeah. So, firstly, there are systems in which the range of clock frequencies is small. You know what the clock frequency is, but not exactly, of course, simply because it's from a physically different device and it won't be exactly same as what you produce here. So then, you have to ensure that the tuning range is not so much that it goes from, let's say you want to lock to 10 gigabits per second data, your VCO should not go all the way to 5 gigabits per second. In fact, it's hard to make a VCO do that. Okay. So just by limiting the range, you can ensure that that won't happen. Now, there is a class of circuits in which you have a wide range, wide locking range. In that case, you have to take other precautions. Okay. I mean, maybe you can't use this phase detector, or maybe you have to have another, like some other circuitry which will watch for this harmonic locking and so on. Okay. So, but see, if you design something for a certain frequency, it's not likely that it will suddenly start oscillating at half the frequency and goes and locks there. Usually what you do is, let's say you are making a 10 gigabits per second receiver. Now you make your VCO oscillate at 10 gigahertz. Of course, you can't make it oscillate exactly at 10 gigahertz. There will be process variations and so on. So maybe you cover for process variations, and also you cover for some mismatch between the transmit and receive clock frequency. Okay. So maybe what you do is you make it 10 gigahertz plus minus 10% or 20% or something like that. So in that case, you don't have this problem of harmonic locking. Okay. In fact, at very high frequencies, especially, it is hard to make 10 gigahertz VCO on its own. And it's very hard to make something that oscillates at 10 and also at 20. Okay, with such a wide tuning range. So this is just kind of the bare bones clock and data recovery circuit. A real system will have may have extra things. Okay, it may have something else to first. It behaves like a frequency synthesizer. That is, it has a periodic reference input. Okay, so in the transmitter there is a reference frequency. In the receiver also there is a reference frequency, but this is not exactly the same as this. Okay, if you make two crystal oscillators, those frequencies will always be different. So what you first, this whole loop works like a phase lock loop, regular phase lock loop. It simply uses the periodic input and brings the frequency close enough to the data frequency. Then you switch over from that phase loop to this loop. Okay, you keep the VCO and the loop filter and everything the same. You simply switch the phase detector and you switch the input. The input, instead of being the periodic signal, it will be the data. So then it will lock to data. It has come close enough to the data and then you lock to data. Okay, that's what you normally do. Any other questions on this linear phase detector? What problems do you see with this? Practical problems.
Like after setting the clock and the setup to whatever is if the density is highly decreased, highly decreased very low. So there may be problem with the changes of the clock. It may shift a lot to the some other because it is not comparable.
That's true. So, I mean, it's not to say the density is reduced, but basically, yeah, this is known as consecutive identical digit, right? You have a large number of identical bits. So what happens is now the loop filter is not getting the correction anymore. Okay. The loop filter voltage on average equals the correct value required to get the right frequency. Okay. It does not mean that at every instant it is at the right value. So maybe at this point it is at some value. Okay. And if you don't have any transitions at all for a long time, what happens is the VCO frequency is slightly different from the data frequency. Okay. So the transitions will keep on shifting. So at some point it will just start sampling in the wrong symbol. Okay. What I mean to say is, let's say we have this, we have a long period without any transitions. Okay. And let's say these are the bit intervals. Now, after this transition, the voltage on the VCO control input is such that the frequency is maybe slightly higher than the actual frequency of the data. That is definitely possible, right? Because, see, the output of, just as we discussed now, the output of the charge pump is not identically zero. It is these up and down pulses. It is the response to the up and down pulses. So the VCO control voltage will have the correct average value, but it will have some ripple about it. Okay. So let's say the frequency happens to be slightly higher. So once there are no, at the point where there are no transitions, it will not have any ripples. It will just hold it constant at that value. So what happens is, maybe initially it is here, next it will shift slightly, and it will shift even more and more and more. And if you have a long enough number of identical digits, a long enough string of identical digits, it can even go to one previous bit. Okay. So there is that problem. So that means that, what does it mean? You have to limit the number of consecutive identical digits. Okay. So every clock recovery circuit can be made to fail by having a sufficiently long string of identical digits. Okay. So this is without any other practical problem. This is with everything being ideal. You simply have ripple in the control voltage. So when you leave when the transitions stop, it can be at the exact value needed, or it can be higher, or it can be lower. Okay. So that will accumulate phase error over the consecutive identical digits, and they are not corrected for because you don't have any information when you have identical digits. Okay. So if you have a long enough string, now the number of cycles counted by the clock can be different from the number of cycles that actually happened in the data. So the next time you sample it, you have a wrong, in fact, you are getting the wrong number of digits out of the clock and data recovery circuit. Okay. So I keep saying clock and data recovery circuit. Where is the data here? So the circuit is supposed to recover both the clock and data. Where is the recovered data? So I can just take not this one, right? It's this. So it is timed at the center of the clock edge. So I can either use this or this one. Okay. So this circuit does both clock and data recovery. So traditionally you would try to recover the frequency of the clock and use another circuit to correct the phase of it and recover the data and so on. So this one does both. It aligns the clock correctly to the correct frequency in phase and also gives you the data output. Okay. So yeah, that's true. If you have a long string of identical digits, you will have a problem, and how long it is depends on the design of the phase lock loop, right? So if the ripple in the control voltage is large, if the design is like that, then what happens is, when you start with the string of identical digits, it can be far away from the clock frequency can be far away from the data rate. So in that case, you will accumulate phase error soon. Okay. So this is related to what you are asking, that in this case you will have this, it's not reference feed through, but this kind of jitter in the clock. Okay. So if you have too much of that, then you will have, you cannot tolerate long string of identical digits. Okay. Yeah. Okay. So as far as practical problems are concerned, so there will be a delay in the flip-flop. Which delay are we concerned about now? Clock to Q delay. Okay. And what else? The delay in the XOR. Why does that matter? Does the clock to Q delay matter? It does? So we have another clock. So let's say the flip flops are identical, so the clock to Q delays are the same. Is there a problem or no? With the clock to Q delay? No, I am saying it is the same. Let's say we are operating with data input with no SI, but we still have to recover the clock. Is there an issue with clock to Q delays or no?
Sampling bit on that clock.
Yeah.
That should be less than that is the data must come on the first flip flop before you have the inheritance.
Yeah. And so
that comes
see, in a clock and data recovery circuit, when you start up, there is no, you can't say what it is, right? The clock frequency can be different from the data also.
all I'm telling is,
Yeah.
first flip flop you are sampling at the positive.
Yeah.
And the data must come to the input of the second flip flop before the anything of the clock.
Oh, you mean the clock to Q delay must be less than half a period? Less than half the period. Yeah, that will be there, right? Otherwise, you could probably not design the flip flop very well. Okay. So that is a very huge error. Yeah. So, but even other than that, is there a problem with the phase detector if the two clock to Q delays are identical, or is no? No? How did you change your mind? Does it? What is the phase? What is the time difference between these two edges? So it's the phase difference between data and clock plus the clock to Q delay. Okay. So because this is phase, I'll say the phase of clock to Q. It's basically the clock to Q delay divided by the time period times 2 pi. Okay. What is the difference between these two edges? What is it? It's pi, right? Pi, that's all. Because the clock, these two edges are separated by pi. And this is delayed from this by something, and this is delayed from this by the same thing. Okay? So the difference between these two is always pi. Is this okay? Huh? So what I am saying is, see, this and this are separated by 180 degrees. Okay? Rather the clock is the same, but this is the inverted edge. So I'm assuming that the clock has 50% duty cycle, so that is separated by half the clock period. Now, the flip-flops have the same delay. The two flip-flops have identical delays. So, this is delayed from this by the clock to Q delay. This is delayed from this by the clock to Q delay. So, the difference between these two is the same as the difference between these two. Okay. So, there is a problem with the flip-flops delay. Okay. What does it do? What is the effect on the phase detector? Characteristics? Huh? There will be an offset. There will be a phase offset. Okay. So that is one of the issues with this phase detector. So the advantage is it can work for high speeds. It's a simple circuit, etc., etc. But the disadvantage is that it can have at extremely high speeds, when the clock to Q delay becomes comparable to the, let's say, clock to Q delay is a significant fraction of the time period, then you have a significant phase offset in the phase detector. Okay. Yeah, the input to the XOR should be at different times, right? Otherwise, the XOR output will be 0. Now, what I am saying is, see, the separation between these two edges, it should have been the phase difference between data and clock. Now, it is not data and clock, it is data and clock plus the clock to Q delay. Okay? So, that's the issue. What about the delay of the XOR gate? Is that a problem? Yeah, so it's not the XOR gate delay is not a problem. Assuming the two XOR gates are identical, that's not a problem. Okay. So in the assignment, you are asked to plot the average, that is the average of the up minus down, okay, versus the phase shift between data and clock. And depending on the clock to Q delay you have, you should be able to see the offset. Okay, you may have to simulate at many points near the zero crossings to see the offset properly. That is, the way to do the simulation is, let's say you hold the data phase fixed and the clock phase varying. The steps in that variation must be small enough so that you catch the offset, but you should be able to see that very clearly. Okay. So there are improvements to this, and basically improvements in one of the ways is, see, when this is operating correctly, that is when the clock is aligned to the middle of the data, the up pulse is half period wide and the down pulse is half a period wide. So the control voltage ripple looks something like this. Okay. So whenever there is a transition, there is a roughly triangular ripple on the control voltage. It is triangular because it's more or less an integrator because of the large capacitor. Okay. So there are ways to reduce the area of this and so on. Okay. The disturbances in the VCO are related to the areas under these pulses. So if you try to reduce the area of that, you get rid of some of the jitter problems in the CDR. So it's in one of the suggested, one of the papers that I suggested for a presentation. Maybe one of you can present it. Okay. If you shift the yeah. Yeah. Yeah, possibly. How do you do that? How do you shift the up pulse? Yeah. See, you can do all of that, and one of the things with high-speed circuits is generally simplicity works, right? So now if you have another flip-flop on top of this here and clock it with this, the delays in those flip-flops and so on will not give you the half period shift, it will give you something else. Okay. Subtract the waveforms. Then, no, that's what happens, right? I mean, when you have two current sources in opposite direction, when it goes to the loop filter, it's already subtracted. That's not. What he was saying was, instead of having this separated in time, you have it time aligned, so that more or less for the entire period they cancel out. Okay. Okay, we'll wrap this up in the next class and see another kind of phase detector that also has gained popularity, especially at high speeds. Okay, that's a more of a digital type of phase detector. It only tells you whether it's early or late. It won't give you an output that is proportional to the phase difference.